Another video in the series on Hopper on 6502. This one is a detailed exploration of the features of the Hopper 6502 assembler. Now, I'm assuming you've seen other videos in this playlist already on your Hopper in 6502, and I'm going to start from the sort of Hello World app that we built in the earlier videos to start talking about the features of the assembler. And we can walk through them as we see them. And I've got a list on a piece of paper here that I can tick them off on. Right. You already know from the previous videos that there's an emulator and debugger. So let's talk about the tools first. If I press F7 to build here at the bottom of the screen, we see it going through the tools. So it's pre-processing, compiling, pre-processing, assembling, optimizing, and then disassembling. So it uses the same preprocessor as Hopper, which is why the syntax of these files looks very similar to the Hopper language, and a lot of the high-level features are identical to the Hopper language, which makes it a very familiar syntax to be working in when you're working on assembly code. So I did this because I got tired of switching between, the assembly syntax, which is where hex would be a $ in front of something, or, comments would be with semicolons, where using indices on things was in parentheses rather than in square brackets, that sort of thing. So I changed the syntax to be more like the modern semicolon and curly brace languages, so that you're not switching between two different syntaxes when you're switching between Hopper and assembly. So, so you know about these four tools. You know about the emulator. You know about getting the runtime built and up running on your if you're using an Arduino device to run a retro shield, or just burning it into a ROM. So let's talk about namespaces. So most assembler tools don't have the concept of namespaces, so that you can encapsulate functionality into different modules. And in this case, just because it's the same as Hopper, it's got programs. And if I right click on this here, it's got units. So there's a serial unit. So everything related to serial is in the serial unit. And this means it can have public and private functionality. So you want private functionality so that it doesn't get used by mistake. So this unit includes a device, and you can pick between the different devices available. So this device here is the one that's emulating the Apple One for essentially keyboard and screen, which is really serial port, serial I/O. And if we look at if I right click on it, we'll see that its unit name is serial device. They're all called serial device, so that you just include it. And then from here, when you want to call a method in that, you can qualify using the namespace, which is the namespace is the same as the unit name. And the lowercase there means it's private. So you can't call this from somewhere in your own program. So you wouldn't be able to call that serial device initialize by mistake from your own program. So just like the Google's Go language, the first character of an identifier needs to be an uppercase or a lowercase character. And if it's uppercase, it means it's public. And if it's lowercase, it means it's private. So why can the serial unit see a private method of the serial device unit? Well, that's because another feature that I've taken from other platforms is the concept of friend. So this unit serial device can say that the serial unit can be its friend, and a friend can see private members like methods, constants, that sort of thing. All right, so that's how namespaces work. It also means you don't have name clashes when your project scales and you end up with a large project. You don't have conflicts in names if you use the same name over, for a second time, a common name inside your unit. If you keep it private, it doesn't matter. So that's what namespaces do. And just like Hopper, you don't need to qualify. So if I get rid of the word, so I'm qualifying these methods here. I don't need to if they're unique. So it'll still build. But it is sometimes worthwhile to put them in for clarity. So I'm qualifying them like that with the namespace to say use the ones in there in case there's a right char in a different namespace and I don't want to call the wrong one by mistake. The compiler should warn you if it's got an ambiguity between more than one. So there we have it. That's what else can I tell you about namespaces? Yes, constants and data, both of which are really constants. So you see one at the top here. It looks like C# syntax, and that's putting data into your program. So we can go look again at that. If we look at the assembly listing that was generated when I built, which should be over here. Maybe it's not. Oh, listing, not ASM. There we go. So we can see at the top of this listing, that's where the data is. So inline data is done this way, and you can do just bytes as well. You can do an array of bytes as well as you can do a string. And if you do a string, it automatically null terminates it for you, which is convenient. So that's how inline data works. Constants are done this way. And all the zero-page ones for these are the zero-page constants for the Hopper runtime. And you can put expressions in them too, like the most obvious expression is to use a different one, to assign one constant to another with just a different name. So constants are done that way. Here's a uint constant as well for an address, which is, referring to something in somewhere else. Like I've got a single place where I define all these addresses, so you only have to change it to one place when you update your program. So if you want to move your serial input buffer to somewhere else, just change it in one place. Here. And I'm right-clicking on things to jump to them, and ctrl+backspace to jump back to where I was. And another thing you can do is, if I right-click on this definition, it'll take me to it. And if I want to alternate between this one and the previous one, it's ctrl+tab. Just switches between the two. Yeah. So I can right-click on anything you can imagine should have a definition or a path, like to open a file. I can right-click on, that's part of the development environment that works in Hopper as well. So all of these things, we're using the same editor as Hopper, we're using the same preprocessor as Hopper, so we're inheriting all the features and functionality of Hopper. All right, so we know about data, we know about constants, friends, public methods. They look like methods, but unlike a high-level language, there's no arguments and there's no return value, because in assembly you can decide to do that any way you like. So you can pass arguments and registers, you can use the stack, you can get your return value via the stack or via register. So it didn't seem to make sense to ever put a type in here. And in fact, if you try and compile it with a type, it should give you an error. So at the bottom of the screen we see the error empty buffer, no return type in assembly. And if I double click on it, it takes me to the error. There we go. So it won't let you do things that don't make sense. Now, another thing, let's look at the structure that you get as part of the. Let's go look at our main programming because we've worked through that before. Being able to put if statements in and loops, right? It makes a lot of obvious choices for you. So when you say if the zero flag is set, do this. You're actually saying the opposite. You're saying if the zero flag is not set, jump past here. That's the logic, right? So let's see what that looks like unoptimized. Turn off the optimizer and look at it. So what did it do? It said if the zero flag is set, in other words, if branch if equal, jump forward by 3. And then on the next thing it said, okay, that means break, jump out to 2CE over here, right? And then after that, it was like, okay, continue, like jump over that and carry on round. So there's a hell of a lot of jumps in here, right? Look at all these jumps, way, way too many, right? But that's kind of what the assembler does. It does the sort of verbose version. And it does the version that doesn't rely on this branch. It doesn't allow this branch to ever exceed 127 plus or minus 128. So it doesn't exceed the range of a single byte branch. And then it leaves it to the optimizer to do the sensible stuff. So let's do that optimized, right? So now when you look at the next version, it's got a lot less branches. So it does exactly what I was saying. It actually branch on the 0 flag being set. What are we looking at? If 0 is set branch forward by 7, that looks the wrong way around. Oh no, it's break. I see what it's done. It's even smarter than that. It's combined it with the exit jump. So it's jumping forward to there. It's actually just breaking in one line. So the optimizer saw all that and said, you know, you said if 0 breaks, like, okay, one instruction, 2 bytes, we're done, we're out of there. Super efficient. And then it's got only one more jump instruction, which is the loop one, which jumps back around to 1C to do the next one over here, right? So yeah, super efficient. For a moment, I was looking at it, it looked wrong to me. It was like, optimizer's too smart for its own good. So now let's see if there's no 2 byte branch instruction if you're using the old 650, the MOS 6502. But if you're using the newer version, as in the one that came out also in the 70s, but 4 years later or 2 years later, if we build that, we're seeing some interesting stuff from my experimental work in the optimizer. Let's have a look. So now that long branch got replaced with a short branch here. So the long jump, the 3 byte branch jump got replaced with a 2 byte jump. And so did this one at the end of the program that loops right around to the beginning. So depending on which CPU you're targeting, it'll use different instructions, and it'll take advantage of the 2 byte instructions when the range is less than the limits. If the range goes over the limits, then it'll use the longer jump. And if it's a conditional jump, it'll do 2 jumps so that it can, still. So you never have to worry about the range of jumps in these loops and if statements. Let's switch back to that before I forget. So you say which CPU you're targeting. The other thing you say is how big your ROM is. Because usually when you program in assembler, there's the origin statement to say where does this start. And, you know, if I'm creating an Intel hex file, what should my Intel hex file look like? Well, I figured that mostly what we do is we put the ROM at the limit of the memory range, which for the 6502 is at the upper end of the range, and for the Z80 is at the lower end of the range. And you sort of shoehorn it into that edge of the memory range. So all you really need to do is know how big it is. So again, if we go and look at the assembly, it's a 1K ROM, so it starts at 1K shy of the end of the memory map, and at the end it'll have the vectors in where they're supposed to be. And if you don't have interrupt handler for non-maskable interrupt or for IRQ, it won't set those vectors, which is entirely legal. And they've got predefined names like that. That's not going to do very much other than just return. So we could give it an instruction just that does nothing. I don't think it will just push A and pop A. It's not going to, it won't optimize that away. Because, well, yeah, let's see if it does. So yeah, now we have a hello IRQ here, which does that push A and pull A, and followed by a return from interrupt. And if we look at the end of the program, it'll be in the vector, it'll jump to that location now. So it automatically does that for you. It automatically sets up the vector if you used it. Another thing it does, suppose I wrote myself a function to print like that. And all this function did is took what was in the A register and did a right chart. So I just made myself a print function. And did that with it. It doesn't do very much. Use it again over here. And let's look at the assembly. So my print function did something sneaky. It does all these optimizations that most people who've been working in 6502 assembly are very familiar with. So it jumps to a subroutine called print. And then inside that subroutine, it's supposed to jump to a subroutine called serial write char. But the next instruction after this jump was return. And we can see that if we, let's go back. If we turn off the optimizer. So yeah, it was jump to subroutine followed by return. And the obvious optimization for that is if the next thing that happens after your jump to subroutine is a return from subroutine, I mean, then you might as well jump there directly and then you'd only have one return from subroutine, so you can optimize this away. And that's what the optimizer does. And it does a lot of that sort of thing behind the scenes. A lot of these obvious optimizations that make sense if you've been familiar with working with 6502 assembly. Let's turn the optimizer back on. All right, let's go and yeah, it does dead code removal, obvious dead code removal. So if I did a return over here, which I can do that way, or I can just do it like that as well. So if I built that, we can never reach that code. So it's gone. It just got rid of it. Didn't include it here. Okay. It does dead code removal. Any code that's unreachable, like if you've got a loop that never exits, normally at the end of the program it has a stop instruction. That stop instruction is gone because it can never be reached, right? So it makes your program as small as possible as well. So dead code removal, short and long jump optimization. That jump subroutine followed by a return gets replaced with a jump. It does some optimization for the 65CO2S, where it uses the shorter instructions where they're available and bit instructions where they exist. So your code gets smaller and faster automatically. So if you code for a 6502, a lot of the time it can do like for example, the 6502, let's do an example. How would we do that? That one might actually do it. Maybe it's already doing it. Let's check. Yeah, it can't. And this is what this is about. It's trying to replace the, I've got some diagnostic messages in the debugger, in the optimizer for myself. It's trying to replace a load 0 with a store 0. Oh, that's actually probably in one of the drivers. Let's have it. It's not actually what we're looking at. So what's it done here? So has it done that? No, it's still load X with here load Y. So let's see if we can force it to do an optimization. So the way to do it would be if you did a load with a very common and then store that at some 0 page variable like top L, right? And then immediately loaded another thing, load, OXFF and store that at top H, right? So if we compile that, let's see what that assembled to. There we go. So for the first one, it replaced the load with 0 to just a store with 0 at top L. So there was a store A preceded by a load of 0, and then obviously the other one I can't do because it's FF. So it combined 2 instructions into one. So it's actually 50% less code, because load A with 0 would be 2 bytes, and then store it into a 0 page variable would have also been 2 bytes. Now it's just store 0 into that page. So that optimization is specific to the 65 CO2S. So if I turned that off, it wouldn't be able to do that. So now we've got the load 0 followed by the store here. So it automatically behind the scenes will do optimizations for the chip that has more instructions. All right. And we've looked at the if and we've looked at the loop. So inside the loop, you can use break and you can use continue as you would expect to. I did a sort of a reimagination of Wasmon to illustrate some of these things. So this is Wasmon, Steve Wozniak's monitor. And then I changed, it's supporting branches, labels for jumping. And it also does the same thing with these in terms of range. If it can do it with a short jump like this, you see, here you go, branch F plus to this next char. What if this was out of range? Like if it was more than 127 bytes away? Well, in that case, it would invert this condition and jump forward by 3 and then have a long jump to there, automatically behind the scenes. You don't have to care, it'll just work. And then loops are kind of useful for places that have multiple exits. So, and you can nest them like that too, and they jump on any condition flag, or if statements on any condition flag. So there's 3 nested loops there. And this structure makes it a little bit clearer than, it doesn't look that clear, but it's a lot clearer to look at than the original spaghetti that was this amazing creation of squeezing this whole thing into, less than 256 bytes. This version is about 260, so it's a little bit over 255. But I did it for purpose of illustration to show how it works. So you can see a lot of use of if and loops. I can get rid of most of the hard-coded branches like this by just using ifs and loops. In fact, the entire Hopper runtime was written with no jumps to labels. So that is here. So the Hopper runtime is relatively large. Depending on, you've got all these different configurations, you can get it to squeeze it into a smaller ROM. And the full version with everything is probably about 12K now. So let's go have a look at extreme versions of. So this here, fast maths, integers, optimizing the obvious circumstances like if you're multiplying by 0, and your thing you're multiplying is 0, just return, you're done. And then these chain of if statements and returns inside there, returns to breakout or breaks to breakout, nested if statements, and then the multiply itself, I find it a lot easier to read. So this is the actual multiply algorithm here down at the bottom. I find this a lot easier to read with the indentation and with the ifs and the breaks and the loops than the original raw version of the assembly of what this looks like. So, a lot of this code is tried and tested, and I've, found using my Google search. And I give credit by just leaving the link in there to where I originally found it. Oh, and here's an example of constants for lookup tables for. This is a fast division by 10, which is very common since human beings are decimal animals. We tend to divide by 10 a lot. So it's got private, hence the lowercase, 2 lookup tables that are here. And we can see how the lookup tables are used over here. So indexing into the lookup table using the Y register. So that's a fast division by 10, and it's kind of handy, a fast division by 10. So these are the fast divisions that happen. The obvious ones are dividing by 1, dividing by powers of 2, dividing by 10. Dividing by 100 is just 2 divided by 10s in a row. Divide by 50, divide by 10, multiply by 2, and divide by 10 again. And you can do that without overflowing 16 bits. And then the sort of stair-step division, regular division, again, I find it a lot easier to understand this algorithm when it's in this structured look than when it's just a linear assembly with spaghetti go-tos. I do far prefer it, obviously. That's why I built it this way. Okay, I think we've spoken enough about the structures. Let me see what else there is to talk about. Right. Constants in expressions. Where can we find some of those? Let's have a look. So the reason I use square brackets for indexing, so if you're doing an index jump, for example, in the syntax, is because the regular parentheses mean something different in semicolon languages. So there's an example. So the regular parentheses around something are an expression. So if you had just, for example, if you had this line, there's a big difference between that and that. So it's probably going to be the most confusing thing to get used to if you are switching to using my assembly tool, is that I use the square brackets for indexing, just like C and Java and C# do, and have done for decades. So very familiar with that as a way to index. So you might do like that sort of thing, or that sort of thing. Whereas this, the round brackets like that mean you've got an expression. But doing a single expression that does nothing is kind of dangerous, because you might think you've done the other thing. So the compiler, the assembler doesn't allow it. So if I try to assemble that, it gives me an error. It says simple expression considered dangerous. Did you mean square brackets? So it'll warn you if you do that by mistake. Yeah. Okay, and then there's one thing we haven't spoken about yet, is a switch. So you can switch on any of the registers. Well, you can switch on A, X, or Y. And it does, for a small switch like this, which only has, 3 cases, like 2 cases and the default, it will actually just do a chain of branch comparisons and branches. Because it's both faster and smaller in code if you've only got a couple of cases to just do a branch chain. But if you have a large chain of branches, or a larger chain of branches, so let's see if we've got a bigger, here's a bigger switch statement, then it makes sense to do this as a lookup table. And that's exactly what it does. So we're switching on the X register here as an index based on these values. And this will turn into a lookup table with an indirect jump. And the amount of code executed is about 6 instructions to jump to any of these. There are a lot of constraints to make this work. If you don't satisfy one of these constraints, it'll simply compile, it'll assemble as a jump chain instead. Part of it is that the code inside each of these switches, it isn't really a switch block, it's just an address because it's a lookup table. So the code inside each of these needs to be a function call. And the last instruction after your switch needs to be the end of your method. So it needs to be the return here, exiting. So what that does is it means this is a function call followed by a return, which the assembler can replace with a jump to the function. Now, if these are all just jumps to functions, it means it can do it with a lookup table, because that's, it's jumping to the functions. The other thing it does is it optimizes the size of the lookup table by truncating 0 values at the end. So 0 values, like if it's not one of the values in that's in a case, then it must be the default value. And that's the other thing. It won't build a jump table if you don't have a default, because that's the place it needs to send all the values of your case variable that didn't meet any of the cases. They need to go to default. So if you put all your constants for your switch statement at the bottom of the range, it makes a very small table. And that's, so for the minimum runtime, I did exactly that. So these are the constants, and I rearrange them so that they're at the start of the range, so between 0 and 26. And that means everything between 26 and 255 are default cases, which means the jump table is pretty small. So it saves space, because your jump table is 2 bytes per case. So that's 512 bytes if you have a full jump table, or if you use the very last slot. So if I had some case in here that used the very last slot, then that'll make the table a lot bigger. Yeah. Anyway, switch is given all those constraints. So let's go through them again. What are the constraints for switch? You have to switch on an index register. You can't switch on A because it's going to switch on. It's going to use that in the jump. So X or Y. You have to. Each of your cases needs to be a method call only, just a method call, nothing else. And the switch needs to be the last thing in your method. It needs to be followed by an RTS, a return, and then it can optimize it. Yeah. There's another example that's a big one, which is the instructions. Same story, last thing after default, it exits the method, and then even when they're not included, they're just doing the default. So all these cases, so this is a lot bigger than the other one, but it makes for very fast execution of instructions for the portable runtime, for the minimal runtime. Because they each just, to jump to any of these is just, about, I think it's about 4 or 5 instructions. Yeah. So this is what the ones that are always there look like. Yeah. Yeah. Right click on things, go to them, see what they look like. Yeah. Okay, so that's the case statement. Been through all of them, I believe. You've seen me navigating in the IDE, so the Hopper environment is more than a language. It's a tool chain, and it includes an editor, debugger. This one for 6502, there's another video in this playlist about the emulator debugger. So there's a lot to this tool chain, not just the Hopper language. Project structure. Same as Hopper. So your main program is this thing on the top right here. The one you're currently in is this file here. If I double click on this, it'll take me to the main one. The main one is called program. And then everything else that I include is called a unit. The way it builds a project is just with this hierarchy of user statements. So there is no project file or no make file. It just, you just wire your project together with all these different user statements, and it figures it out. It's a 2-pass system, and so hence the preprocessor, and it uses the same preprocessor for Hopper and for assembler. So in the preprocessor, it goes and finds definitions. So what are definitions? Definitions are anything that are outside the curly braces. So this method, that method, all the constants, all your data. So it collects all the definitions on the first pass. And then on the second pass, it's either the Hopper compiler or the 6502 assembler. It does what's between the curly braces. And because it's 2-pass, it means there's no such thing as having to have things defined before you use them, or like, forward statements in Pascal, or header files in C. It's a bit more like C# and Java in that way, in that it's a 2-pass system. So, and it's also, most assemblers are not 2-pass systems. You have to define things before you use them, which can make it a little convoluted if you've got 2 things that depend on each other as to how to define things first, and you just don't have to worry about that in the system. Yeah, the conditional compilation symbols are the same as C#, C, and Java, unlike the ones with the dot directives in conventional assembler. So again, you're just in one platform, you're in one syntax that you're familiar with, and you just seamlessly switch between assembler and your curly brace language. One more thing to add. If we go back and to Wasmon again, I was being a little dogmatic about not including labels, because goto being the root of all evil. But eventually you realize that you can't really do the things you want to do in assembly if you don't have labels. So most of the time you can you live without them, but when you're looking at something that's as optimized and convolutedly clever as this as Wasmon, to squeeze so much into such a small space, it was impossible to try and port this into structured format without having labels. So I added labels, and then of course I extended it so that when you're doing a branch to one of my labels, you don't have to worry about whether it's going to be exceed your 127 or minus 128 range. It'll figure that out for you by replacing it with 2 jumps if it needs to. But my concession to say, okay, we can live with gotos and we can put labels in, was that you can only use them for branches. So you can't jump subroutine to them. You can't jump to a subroutine to a label. So only with branches, either conditional or unconditional branches, can go to labels. And then labels, the scope of the label is within the current method. And in this case, it's the main method. By the way, this hopper main method is, you don't have to say that. You can just start with a curly brace. But one of my users suggested we actually put a signature on the start of the main program because it makes it easier to find if the file gets big. But yeah, so you're constrained to only branching to labels that are defined within your current method. So that does, and I did that because the system is sort of method based. So when it's doing optimization, for example, most of the optimization is per method. So it doesn't have to care about what you're doing outside the method. So that's how it can do optimizations like that, replacing load A0 followed by a store with store Z. It can do that because it knows what's happening shortly after that. Shortly after that, you're modifying A again, so you don't need to care what the value is in A. You can just use the store Z function instruction without using load A with 0. You're not relying on the fact that this is 0 in A further on. And it's much easier to do that if you're only optimizing at a method level. At a global level, it'll remove unused code. So it'll remove methods you never called or constants that you never used, data constants that you never used. But so that was the constraint. It wasn't oh, I'm going to be clever about not allowing super spaghetti by jumping from inside one method into another method. It was sort of imposed on me by the way Hopper already works, but it's a good thing. Okay, I think that is all I can say for now about assembler. There is something else. So some people have a difficult time. So if you look at 6.5 DASM, oh, that's the assembler, the other one. Yeah, okay. If you look at 6.5 DASM, this assembler, it's got an extra option here. It's called traditional syntax to keep the OGs happy. So if I 6.5 DASM, the hello program that we wrote, and I just go OG, it's disassembled it. And then if we load it into the editor, load the listing into the editor, it's loaded this listing, and this syntax is the sort of more conventional assembly syntax. So it's using semicolons for comments, it's using a $ for hex for operands, and no 0x for the hex for addresses and bytes of your code here. And it's a little bit more compact. Yeah. So you can, suppose you want to share an assembly listing with a friend who's not familiar with the Hopper 6502 assembler, then you can send them this version of it. And it also, I was going to show if I can see any. I don't see any examples. There's no examples here, but it uses the round parentheses for references here too, instead of the square ones. So there is a way of And if I switch off OG there and then go back again for contrast, this is the Hopper version of it, which is more semicolon and curly brace oriented. So there's 0x for hex right through everywhere. And the comments are done with a double slash, etc. And in this case, the square brackets for the references. Yeah, I think that's the only other thing about the environment in the assembler. Yeah. So there's a lot in this playlist about how to get this up and running on your Windows machine, how to get it running in the emulator. It's designed to be able to make ROM images so that you can build them with an EEPROM programmer, burn them with an EEPROM programmer. Even though all my demos are using this Retro Shield, I also have a 6502 device that I've been burning EEPROMs for. So you can burn EEPROM directly. It generates the Intel iHex format for EEPROM burning, complete with the correct origin position, so that you can get your image onto EEPROM correctly. Okay, let's switch back to something interesting and fade out. There was one up there again. Anyway, thank you for watching. I recommend you watch the rest of the playlist if you got interested in this. And then if you're interested in the Hopper language, there's a Hopper language playlist, which is sort of platform independent, also on the channel. Cheers.